It is my pleasure to welcome you to the crash course Quantitative Research Papers. We have reached the fourth section of a research paper, of a quantitative research paper, methods. And this part is about the sample and sampling and, in this regard, inductive statistics. Before I start, I would like to point out that I differentiate between inductive statistics and inferential statistics. I know that some use these terms interchangeably. However, I see inductive statistics in the relationship between sample and population, whilst inferential statistics, I will explain statistical procedures like the t-test, chi-square test, regression, and so on. But let's start what a sample is. To understand a sample, we need to understand what the population is. And the population consists of the persons or other entities like companies, organizations, for whom the results or the data we are collecting is valid. The sample is then the data we are collecting, or better, the people from whom we are collecting the sample. You can distinguish between the gross and the net sample. Gross sample, that would be all the persons we are contacted and asked to give us information. But not everybody will answer our questionnaires. Therefore, we have the net sample, and that is what is essentially of relevance. The net sample consists of all the persons from whom we collected data. In the context of population sample, you have two approaches: a complete survey and a partial survey. A complete survey means we're collecting data from everyone, from every person or entity of the population. That might come a bit costly. So just looking at the population of the UK and the age group of 18 to 65 years, that is 40.5 million. That is never in a million years in a budget to collect data from all of the people. And furthermore, not everybody will be happy to answer our questionnaire. Therefore, we have normally partial surveys, and this is the data we're only asking our sample, a selected person. In this context, a basic concept is a representative sample. Quite often, a representative sample is confused with just a number. The larger my sample size, the more representative it is. That is not quite correct. The definition of a representative sample is: sample is representative when the distribution of attributes of the sample resembles, so it's roughly the same, as the distribution of attributes in the population. Only then a sample can be called representative. Perhaps the numbers here on the bottom will make this a bit clearer. So let's assume we want to get some information about the population of the UK in the age of 18 to 65 years. So our population would be 40.5 million. We contact 4,000 of these people to ask them to fill out our questionnaire. That is our gross sample. But not everybody answered our call, so we only collected data from 2,000. That is our net sample. For a representative sample, it is important that the distribution of attributes within our 2,000 that we have data from resembles the distribution of attributes in the population, the 40.5 million Englishmen and women. Let me give you a few insights into sampling procedures. To understand sampling procedures, you need to understand research approaches. You can distinguish between two. You can, of course, distinguish between more, but I think these two will explain how you go about research and then the sampling approaches the best. You have rather exploratory designs or rather representative designs. Rather exploratory designs ask if there's principally an effect. For instance, does A principally has an effect on B? So, standard example, which is researched uncountable times, does work satisfaction have an effect on organizational commitment? We just want to know, is this principally the case? Then we do not need a representative sample. And look at research papers, at articles in research journals. Most of them do not have a representative sample. And fair enough, they just want to look, is this principally the case? Can we principally say this theory that we're testing is okay? Happy days. As a rule of thumb, I advise you to have at least 200 participants within your sample. There are other rules of thumbs, but I believe that is a very solid one. And of course, larger sample size is not a shame. It is okay to collect data from more persons. Now, representative samples. There, where we need a representative sample and representative designs. For instance, election polling. What party would you vote for if we had a general election today? Then we want to have a sample that resembles the people who are eligible to vote. Against this backdrop, coming to the sample procedures. There you can distinguish between non-probabilistic sampling and probabilistic sampling or random sampling. Non-probability sampling, for instance, convenience sampling. You just collect data from whoever you can get hold of. So whoever you know, get the data from. Happy days. That is what you quite often find with rather exploratory designs. And it's fair enough, you can do this. Where you can get to a rather representative sample, an approach is quota sampling, but it's still a non-probability method. Now, a probability method or random sampling you have when each person or entity of your population has the same probability or chance to be selected into the sample. First, let me give you an example of what is not a random sample. So that is what I've sometimes heard from students. They said, I had a random sampling course. I sent my emails out, my questionnaire link out to my friends, and they sent it out to other friends and to others and to others to spread like a snowball system or an avalanche. And I had no influence, no control to whom they were sending the questionnaire link, so it was all probability random. No, that is not a random sample. Of course, the friends of this person who conducted the questionnaire had a higher probability to get into the sample. Then their friends got a higher probability to get into the sample. Just to make this clear, assume you're living in the south of England and you grew up there. Most likely, the majority of your friends will also be in the south of England. And then your sample will be very heavy on southern Englishmen and Englishwomen. People from Scotland, Northern Ireland, the Midlands, they have a lesser chance to get into your sample. And then, not every person of the UK has the same probability to get into your sample, then it's not a sample that's representative for the population of the United Kingdom. Now, let's go to the sampling procedures, and I would introduce you first to quota sampling. So what you do is basically 4 steps. First, you define the attributes that we use for your quota. They should be of relevance so that you, with your sample, can resemble the population. Then you're determining the distribution of the attributes in your population. You define the sample size, and then you can calculate the quotas. So I use the simplified example, population of England, in the age groups 20 to 29, 30 to 39, 40 to 49, 50 to 59. So we know from statistics, official statistics, how the distribution is. And in total, we have 29,746,870. The distribution we can determine in percentage, so that we know 23.88% are in the age bracket of 2029, 26.06% in the age bracket of 3039, and so forth. Now we define the sample size and say we would like to have results from 2,000 people, and then we can calculate the fourth step. 23.88% times 2,000 is 478. We need 478 in the age bracket of 20 to 29. Second age bracket, 26.06% times 2,000 equals 521. So we need 521 participants in the age bracket of 30 to 39. That is quarter sampling. Next, I would like to come to the sample size. Hardcore statisticians would say what I'm showing you in the moment here, determining the sample size and these equations, you can only apply when you have a random sample. I would say don't be so strict. These equations also give you a good idea about the size of a quarter sample. Now, you can calculate the sample size for an infinite population or for a finite population. Now, one might say, wait a minute, all populations are finite. What the hell is infinite population? And there it's quasi-infinite. There's a rule of thumb. If your sample size, lowercase n, divided by the size of your population, the uppercase n, is more than 0.05, then you straight away can use this, the equation for sampling for infinite populations. And that is, if you want to have results for the population of the UK, the population of London, the population of Manchester, all what goes in this direction, you might use straight away the equation for infinite populations. And with a closer look at these equations, hopefully make clear, they are identical with one exception. So in both equations, you have z times p times 1 minus q divided by delta p squared. It's the same here, z squared times p times 1 minus p, it's p not q, 1 minus p divided by delta p squared. But for finite populations, you have a correction factor. And in the denominator of the correction factor, you have the population size. And if the population size gets very large, the overall correction factor will get very small. Factor again is in the denominator of the overall equation, and then it has virtually no impact on the overall denominator. But I would like to explain this equation in a bit more detail. And here, perhaps the advice or a golden rule for life, equations and mathematics are our friends. So I don't want to see anyone now saying, oh, equations, I switch off. They're our friends. They're just a reduction in speech or in words. What is in these equations? We can also state in long sentences. But with these variables and indicators, we make them shorter and they're more easily to grasp for us. So I will use the equation for infinite population. As I just said, it is just a correction factor to give you the idea how the sample size is calculated. Now, n is the sample size. Z refers to the confidence level, meaning with which percentage do our results in our sample match the results, the true values in the population. P is a distribution that we assume like 50% are voting for party A and so forth. Then 1 minus P is, if you will, the opposite. So we have 50% as a P, 1 minus P is also 50%. That's something we assume at the start. And delta P is the margin of error, if you will, your target range with your accuracy. So you will never be on point. Let me give you an example. First, we assume that we will measure, we haven't measured, but we will measure 50%. For instance, 50% will say, I vote for party A in the next general election. Then 50% will say, I will not vote for party A in the next general election. So that is our first assumption. We have a distribution of 50%. The reason being for taking 50% is that this is, if you will, the worst case for you. It is 50 times 50 is 2,500. And if you have 40 to 60 distribution, it will be 2,400. 70 to 30 will be 2,100. So your numbers will always be the highest with 50 and 50. So 50 say yes, 50 say no. And you'll be on the safe side with your sample size. So come back. We're assuming before we conduct our survey, we have a distribution of 50%. 50% say yes, 50% say no. Then we determine the Z value. That's a confidence level. And the standard is, we want to say with a probability of 95%, our results match the true values in the population. And then from tables, you can take standardized Z values. And for 95%, the standardized value is 1.96. If you want to go to a higher confidence level, like 99%, the Z value will go up and will be above 2 somewhere. I don't know the table by heart. So we take now our Z value and can say, all right, the value we are measuring reflect the true values in the population with a probability of 95%. And perhaps you can see, I've just explained the Z value. At 95%, we have 1.96. You might say, no, 95%, that is not high enough, the probability. I would like to go higher, 99%. Then, from the standardized tables, you take a higher Z value, you put them in your equation, and then a higher Z value will make N, your sample size, larger. So if you will, for a higher confidence level, you buy with more participants, with a larger sample size. Now, at this point, what we have in from our equation is the probability, the assumed distribution, 50% times 50% in our example, and do this as a general rule, and we have the Z value, in other words, the confidence level. With 95%, our values match the true values in the population. Now, you will never be on point, exactly on point. If we will measure 50%, the true value in the population will not be exactly 50.0%. It might be 51% or 50.05%. It will never be. We will never be exactly on point. And there the margin of error comes into play. That is, if you will, the target range or the hit range that we allow. And the standard is 3%. If we put this into our equation, we say, now, with the step before, with a probability of 95%, the true values of the population are in the range of plus minus 3% of our measured values, meaning there will be in a range between 47% to 53%. We can say, if we measure 50% with a probability of 95%, the true values are somewhere between 47 and 53%. In other words, we are right with a probability of 95%. If you put these values into the equation, your sample size will be 1067. And that is a magical sample size number. And this is also the reason why you quite often find in election polling that the sample is always slightly more than 1,000. And the reason for this is this magic 1067 number. Now, you do not need to calculate, so you know the 1067 number for these samples, you're on the safe side, but you might not have an infinite population. Then you do not need to calculate these equations, or the equation I showed you before for finite populations. You can use internet tools. You put in your numbers and they will give you out the sample size. Now that already was inductive statistics that you use before you conduct your survey to determine the sample size. You can, however, also use inductive statistics after data collection, because you will not measure 50%. So think again, election day, so political polling, there are more parties out there than just two where you might think is a 50-50 race. And then you see one party gets 20%, the other party 30%, the next 10%, and so forth. And then you can use this equation. You have your sample size, and you solve the equation to Z, and then you know what confidence level you have. And if you have done, or if you have put in 50% before as a distribution, you are on the safe side, and your confidence level might even be better than assumed. So inductive statistic, the core of inductive statistic is the question with what probability and margin of error, so the range where you hit, do the results of the sample reflect the true values of the population. So, and here I hope I could give you a solid understanding of how you conduct sampling and what a sample is and what a population is, and what in its core, and what equation you basically use for inductive statistics. The next part will be dealing with the scale of measurement, which is the precondition to understand descriptive and inferential statistics. Until then, I wish you all the best, and it is bye-bye for now.